In this video, I would like to define the trigonometric functions in the complex numbers, specifically sine of z, cosine of z, and tangent of z, where z is the complex number x plus iy. The derivation of sine of z and cosine of z uses Euler's formula, which I will be assuming in this video without proving. I already made a video proving Euler's formula, so if you need a review, I'll include the link in the description. So here's how we derive sine of z and cosine of z. Recall that Euler's formula is e to the I theta equals cosine of theta plus I sine of theta. If we substitute z for theta, we get e to the iz equals cosine of z plus I sine of z. If we substitute negative z for theta, we get e to the I times negative z equals cosine of negative z plus I sine of negative z. We can rewrite the left-hand side as e to the negative iz, and cosine of negative z equals cosine of z by the negative angle identity for cosine, and sine of negative z equals negative sine of z by the negative angle identity for sine. So e to the negative iz equals cosine of z minus I sine of z. So we end up with this system of equations in terms of sine of z and cosine of z, and what we would like to do is to solve the system of equations so we can derive a definition for sine of z and cosine of z in terms of the exponential function. If we add the first equation with the second equation, we get e to the iz plus e to the negative iz equals 2 cosine of z, since the I sine of z term cancels out with the negative I sine of z term, and if we divide both sides of the equation by 2, we just get cosine of z equals e to the iz plus e to the negative iz over 2, and this is the definition of cosine of z in terms of the exponential function. If we take the first equation and subtract the second equation, we get e to the iz minus e to the negative iz equals 2i times sine of z, since cosine of z minus cosine of z just equals 0, so the cosine term disappears, and I sine of z minus negative I sine of z equals 2i times sine of z. So if we divide both sides of this equation by 2i, we get sine of z equals e to the iz minus e to the negative iz divided by 2i. So this is the definition of sine of z in terms of the exponential function. Sine of z equals e to the iz minus e to the negative iz over 2i. So this is how you define cosine of z and sine of z in terms of the exponential function, where z is the complex number x plus iy. Tangent of z is defined by sine of z over cosine of z, just like in the real numbers. So we just have to plug in the definitions of sine of z and cosine of z that we just worked out to find a definition for tangent of z in terms of the exponential function. If we plug in the definitions of sine of z and cosine of z in terms of the exponential function, the expression becomes e to the iz minus e to the negative iz over 2i divided by e to the iz plus e to the negative iz over 2. If we multiply both the numerator and denominator of this complex fraction by 2i, the expression becomes e to the iz minus e to the negative iz over I times parentheses e to the iz plus e to the negative iz. Since tangent of z equals sine of z over cosine of z, we need to ensure that the denominator, cosine of z, is not equal to 0 so that we are not dividing by 0. This means we need to ensure z doesn't take on values which make cosine z equal 0. The values where cosine z equals 0 are the values of z in the form pi over 2 plus k pi for all integer values of k. So the domain of tangent of z is all complex numbers except for pi over 2 plus k pi for all integer values of k. So these are the definitions of sine of z, cosine of z, and tangent of z in terms of the exponential function. And we also have to keep in mind that tangent of z has a restricted domain and is not defined for z values in the form pi over 2 plus k pi for all integer values of k.